Swayam Prabha. Digital India. Educated India.
Hello, we continue with our discussion of functionals involving two variables, that is independent variables like x and y, meaning that we are looking at problems where the domain of the functions that we are trying to find is actually in 2 dimensions. We had discussed at length about single variable functions such as y of x or several functions y1, y2, yn. Now we are discussing functions that are that depend on 2 variables x and y. So, we make it z as a function of x and y. So, let us continue with that and solve couple of problems. So, we appreciate how to deal with 2 dimensions and also an example for 3 dimensions which we had discussed in the last lecture. So, looking at this, we are looking at functions functionals involving 2 and 3 independent variable, that is what we call them, like x, y, z, which are the ones that form the domain of the functions we are trying to find. So, what we will discuss in this lecture is what we had already discussed, that integrand is a function of z and zx and zy. In our notation, zx, if we recall, is dou z by dou x, and then zy is dou z by dou y. So, we have a functional that depends on x and y, which we write like a dA, that is, if I take an arbitrary domain like this, somewhere I take a small area which I am denoting as dA, and then I integrate over the entire area. That is what this means. That is our j, the functional, which you minimize with respect to if I write, we are minimizing with respect to z, x and y. Okay. That is our problem. We discussed that and the boundary conditions, we discussed it in the last lecture. Today we will do a problem that uses that, and we will also consider a case where our functional, again another j, which depends not only on zx and zy, but also depends on zxx. Based on the same notation, you can imagine what zxx stands for. It stands for second derivative of z with respect to x twice. So, we can also write zyy, that is dou square z by dou y square, and then we can also do a mixed derivative zxy, that is dou square z by dou x and dou y, or dou y dou x, right. So, we also look at this. After that, anything else you should be able to do it on your own. Okay. And in fact, we do not encounter problems that involve more than second derivative in engineering and normally physics applications. Okay. So, this is what we will do, and we will do examples of both of these cases in geometry and mechanics, and that also translates to design or structural optimization. Okay. So, just to recall, when we have the functional that depends on zx and zy, again the notation is given here, z sub x, z sub y. We take the variation, I am just reminding so that you can see how we do when there are higher derivatives zxx, zyy, zxy. We take the Gatu variation like this, equate to 0, and then we try to eliminate, not try to, in fact we eliminate delta zx, delta zy, because delta z is the variation, right. So, this is what we called as variation of z, small perturbation on z, but here we have partial derivative of variation with respect to x, partial derivative of variation with respect to y. We need to do integration by parts, we do integration by parts. Anyway, that is in 2 dimensions, that is in 1D. In 2D, it basically means applying Green's theorem. Okay. Then that gives us the differential equation as well as the boundary conditions. So, how does the differential equation look like? Again, let us remind ourselves that integrand here is a function of z, z sub x, z sub y. Okay. So, this gives us a differential equation, that is dou f by dou z minus dou by dou x of dou f by dou z sub x, that is wherever z x is, only that partial derivative you take, and then take partial derivative of that with respect to x, dou by dou y of dou f by dou z y equal to 0. So, this is the differential equation. This is the differential equation. Okay. If you actually compare this with when the functional had only one variable like y and we had y prime, right. When we had that, the differential equation, what we call Euler-Lagrange equation, was like this: dou f by dou y prime equal to 0. Again, if you recall, y prime is dou y or even just dou y by dou x or dy by dx, right. That was y prime, and you can see the similarity between these two. Okay. But we also know how to derive them. So, differential equation is easy to write, or what we call Euler-Lagrange equation. The boundary condition requires little work, which we did last time, and through integration by parts, which is Green's theorem, applying that is a little trick to eliminate the delta z sub x, delta z sub y. We got a boundary condition which is shown over here, right. So, whenever delta z is 0, that is z is specified, then the boundary condition is satisfied. When it is not specified, what we call this one is the Dirichlet boundary condition, or what we call essential boundary condition, meaning that Dirichlet or essential boundary condition where z is specified at a point on the boundary or a portion of the boundary, then there delta z is 0, the condition is satisfied. In other place where it is not specified, we get this. This is called the natural boundary condition or Neumann boundary condition. This is boundary condition BC, boundary condition, and that here means this. Okay. So, that is what we had derived last time. Now, let us actually take an example that illustrates what we have just done, okay, where z should be integrand should be a function of z, z sub x, z sub y. And this is the problem that soap films solve naturally, right. If you take a loop of wire such as the one that is here, okay, that is just a loop of wire. You should try this experiment at home, and all you need for that is basically a wire that is easily bent. So, you take it and make it a loop, and in 3 dimensions, you does not need to be 2 dimensions, make it into 3D, dip it into soap water and take it out. Then you will see a surface such as what we see here, a surface forms, right. That surface that the soap film forms is a minimal surface, meaning that you will be minimizing the area here. This is the area of the surface, whatever area that we see here, that area will be minimized, and that area is given by the expression that is shown here, square root of 1 plus zx square plus zy square. Essentially this is to say that we have, if I take a little patch here, little patch, and we have to integrate over the entire surface. The little patch is given by this 1 plus zx square plus zy square. Okay. So, when we have this expression of minimizing area, you can see that integrand now depends on z sub x, z sub y. Okay. Z does not appear here, but does not matter, we can still apply. It is just that in this problem this is equal to 0, whereas this and this are not equal to 0, right. Those things, in fact, how much that is, we have here dou by dou x of this part and dou by dou y of this part. So, this is dou by dou x over there and dou by dou y, what is inside is right there. Okay, that is what it is. If you continue the differentiation, you get an expression that looks like this. Okay. This expression basically defines that minimal surface or the surface formed by soap films. Any loop of wire you take, there will be minimal surface, you will get that, and soap films instantly solve this differential equation. Okay. How do they do it? They do not actually know calculus of variations as we know it, but what they try to do is minimize the surface area to minimize the surface energy that they have. Soap films always minimize surface energy and hence the surface area. So, this geometrically if interpret means that the mean curvature is 0. So, what we have here is simply says that at every point on that minimal surface you have mean curvature equal to 0. That is something we need to remember. And again, a calculus of variations only gives you differential equation boundary conditions, but it will not tell you how to solve the differential equation. For that we have to use our usual techniques. Okay, that is one famous problem for this. Now, before we take up a mechanics example where the integrand is depend on two independent variables such as x, y in the domain, let us actually consider a case where we have now these second derivatives also, z sub xx, z sub xy, z sub yy, which we had already defined earlier today. Okay. Now, in order to arrive at the differential equation boundary conditions, again take the variation with respect to z, we get everything, and to get rid of these two we apply Green's theorem and get to delta z. Now, if you want to get rid of these other terms, okay, so that is delta z xx, delta z xy, delta z yy, you have to apply Green's theorem twice. Okay, that is all there is to it systematically, and we have to use the same trick where this whole quantity that we have we represent as a term and subtracting another term from it as we have here. So, what I had encircled in the last slide was this, that is split into this term and then this term, okay, because then we will be left with not delta z sub xx, but delta z sub x, delta z sub x. After that we have to do one more time to reduce delta zx and zy to just delta z. Okay. So, that is what we have here, a lot of manipulation. Since the slides are going to be there accompanying these lectures, you can look through and then go through the terms. Okay. So, you have to do some rearrangements and group them together and so forth. When you do all that, you get both the differential equation which is there, this is the earlier one that we had, right, this is the differential equation part. Now, we also have additional terms that will come up. These are the boundary terms, right. So, we have these. We will also get the additional terms for this if we do one more integration by parts. If you see, we have gotten rid of, by doing Green's theorem once, we have gotten second derivative to first derivative. If you do one more time, okay, the same thing. If you do one more time where you replace one term with two terms, now you notice that we have only delta z and not delta z sub x or delta z sub y. Okay. If you do the same thing again, what we get will be all the terms in the differential equation. If you see the first row here, we can observe what are the terms that came in differential equation, dou f by dou z minus dou by dou x of dou f by dou z x, all of that, this and that. We also have the second order term dou square by dou x square of dou f by dou z x x, and same thing is mixed derivative with respect to y also. You just need to work out and accumulate more terms that will go into the boundary. And if you do all that, you will get Euler-Lagrange equation that looks like that. Okay. And you can see a pattern here, just like we try to see a pattern in one variable case. Here also dou by dou x, dou by dou y, dou square by dou x square, dou square by dou y dou x, dou square by dou y square, and the same thing is done on z. This is dou z by dou x, dou z by dou y, dou square z by dou x square, and so forth. Okay. So, we can actually write them down without actually having to do anything, any calculation. Similarly, boundary terms tend to be longer. So, these things what I have not shown here, A, B, C, they are pretty long. You can always take them and write them yourself, okay, just the rearranged terms and looking at it. So, an example that is related to this is a plate. A plate, it is two dimensional thing such as the one we have shown, or a dinner plate for example. You can constrain it on the boundaries or put a knife edge on the boundary and so forth. You can constrain various ways, but what this plate does when there is load acting on it, load is given by this q x y, is that it will deform. So, this plate will deform in some manner. Okay. The deformation that we denoted by w here as a function of x and y, then we get a differential equation. For that, what you need is we have to minimize the potential energy with respect to that function w x y, and in this case for a plate, from mechanics and geometry you can compute the expression for potential energy of a plate. Okay. That has, this is the strain energy that you have up to this point, it is strain energy, and this is as usual work potential. Okay. Q is the transverse load, W is the work done, that should be the work potential. Overall we get the potential energy. The whole thing that we have is potential energy, right, that is what is P E, potential energy. Okay. This is a problem where like what we had considered, right. So, this one it depends on z, zx, zy, zxx and so forth. It does not depend on all of them. There is certainly w, right, and the second derivatives. First derivatives are not there, but that is okay, they just the terms will be 0. If you work this out, writing it all the things that are there, okay, we get an expression. By the way, here d is the plate modulus which is given by this, T is the thickness of the plate. Okay. So, if I somewhere we say some thickness, that is thickness of the plate, E is the Young's modulus, and nu, another material property, is what we call Poisson ratio. Okay. With all of those, we have an integrand that depends on W and its second derivatives. If you write down the Euler-Lagrange equation, then you get what we call plate differential equation, which is given by this. Sometimes for short form we call it del to the fourth, like here. Okay. And the boundary conditions we have to work out quite a bit in order to see what goes in there, what goes in there and what goes in there. But all the steps are there, you just need to work it out for your functional, then you get these things, and then it will be useful to solve any kind of plate problem. There is a set of conditions a plate will have, they are either Dirichlet or Neumann, we can solve those things. And based on whether W is specified, Wx is specified, Wy is specified, we can change the boundary conditions and solve the problems. Okay. That is about 2 variables. Now, we had touched upon the 3 variables, and we essentially say that whatever method we have used for 1 variable extended to 2 variables by replacing integration by parts with Green's theorem. In the case of 3 variables, we replace Green's theorem with Gauss divergence theorem. So, here the function u is a function of x, y and z, okay, and that is the unknown, and integrand here will be function of up to first derivatives u, u sub x, u sub y and u sub z. And when we do all this, again taking the variation and equating 0 and applying Green's theorem, which now becomes Gauss divergence theorem. Okay. So, if we do that, then we get the differential equation. Of course, the trick that we used still remains. The idea is to get rid of this and put it into form of just delta u everywhere, except that there is del dou by dou x here, but we are trying to avoid trouble. Okay. So, either u is specified or ux is specified, the other one will be 0, and then we can go on to write the plate boundary conditions. So, if we do that, we get the differential equation part, delta u is arbitrary, and then we get this, and this one is in the volume integral, which we convert to surface integral by using the divergence theorem. Okay. Divergence theorem is this. So, if you take divergence of a vector, in this case u, del dot u is called the divergence. Okay. The divergence, if you integrate inside the volume, surprisingly it is equal to the flux that is going out or coming in, u dot n ds, which is done over the surface of the volume that is enclosed. Okay. That is what we are doing. We have, if I say divergence, it is basically dou by dou u by dou x plus dou u by dou y, dou u by dou z, and that is what we have here, dou by dou x, dou by dou y, dou by dou z, all of these things. And if we write this the Gauss theorem, if we apply from here, we get here, then we can see what is the individual things are. Okay. That has to be true on the boundary. So, now if we take this problem for the 3-dimensional elasticity case, let us say I have a solid, okay, 3-dimensional solid. It may be fixed somewhere, it may have some forces on the boundary, there could be some forces in the interior also, like weight and centrifugal force. Okay. In that case, we can minimize this, it will depend on the first derivative. We take the linear strain u sub x, u sub y, u sub z, and u itself is a function of x, y, z, and hence u sub x, u sub y, u sub z are also functions of u. Then you get the differential equation. Okay, there is a pattern, there is a dou by dou x, dou by dou by dou by dou. So, you can close your eyes and write these. Boundary conditions also have pattern, but now it is just written in 3 dimensions, because this should be true at every point on the boundary, either that is 0 or this is 0. When is this 0? Whenever u is specified anywhere, okay, and that is how it looks like. For this, if you want an example, the best thing is a solid that I just sketched over here, right. So, we can write down potential energy, because that is what will be minimized, and that is written in terms of stress strain relationship. Basically D here is stress is equal to D times epsilon. All are, you can say is a matrix form, these are in vector form, or all can be in tensor form, and you have that. Okay. Epsilon here is a strain, so and U is the 3-dimensional displacement. We are defining what U is actually, and we can write Lagrange equation. When you write it, you get this familiar thing that we use in mechanics of solids when you look at continuum, and the boundary condition would look like this. Okay. So, that is how we do the 3-dimensional problems also, and as I said, more than 3 dimensions not necessary. In 3 dimensions having double derivatives also is rare, but you can still follow the procedure, work it out. You have to apply Gauss divergence theorem twice, okay, when you have more than first derivative in your integrand. Okay. Just to summarize this, we have discussed 2 and 3 independent variables, 2 and then we have 3 independent variables, and we looked at Green's theorem as an extension integration by parts in 2 dimensions, and there is Gauss theorem to help us in the 3 dimensions. Okay. And we have solved examples of a soap film, and in mechanics we did the problem of plate and the 3-dimensional elastic solid, where the boundary condition, we take a quick look. See, the boundary condition that comes from the divergence theorem, which says that d epsilon, the tensor notation, basically this is sigma. Sigma n, if you write this, let us say the tensor, sometimes we write like that, right, and this is the unit vector. If we do that, that basically says that the traction on the boundary is 0 whenever delta u is not 0. When is delta u is 0? Delta u is 0 when u is specified, like fixing it. Okay. When that is not specified, the corresponding stress should be 0. Whenever you have not specified, then that portion, if there is no force, the force action as it is called in solid mechanics literature, that will be 0. That comes from the boundary condition. So, at this point you should see the power of calculus of variations. We can solve many problems in geometry and mechanics. As we are seeing in this course, we can also use calculus variations to solve structural design problems. In the next part of the lecture, we consider one more concept in calculus of variations and relate it to mechanics and geometry and design as usual. Thank you.